All right, welcome back. Today, we're going to tackle a really fundamental question in computer science, something that's at the heart of so much AI. How does a computer solve a problem when it's completely in the dark? Think about it. No map, no hints, not even a sense of which way is up. It's totally flying blind. This is the world of what we call uninformed search algorithms, and we're going to break down exactly how they manage to find a needle in a haystack, starting right now.
So let's try a little thought experiment. Imagine you're dropped into a huge, sprawling maze. It's pitch black. Your goal is to find the exit. Now, you can feel the walls, you know what an opening feels like, and you'll definitely know the exit when you get there. You'll see the light. But here's the catch. You have absolutely no other information. No compass, no "you are here" map, nothing. You have no idea if any step you take is getting you closer to the exit or just deeper into the maze. This is the exact problem these algorithms are trying to solve. How do you find anything when you have zero guidance? And that right there gets us to the core definition. We call it uninformed search, or sometimes, pretty appropriately, blind search. And it's exactly what it sounds like. The algorithm knows where it's starting, and it knows what the goal looks like. It can figure out its legal moves from any given spot, but that's it. That's all the information it gets. No hints, no getting warmer signals. It can't look at two different paths and say, that one looks more promising. All it can do at any given point is ask a single, simple question. Am I at the goal now? Yes or no? That's its entire reality.
Okay, so given these huge limitations, how did early computer scientists even begin to tackle this? Well, they came up with two very different, you might even say philosophical, ways to approach it. You can think of them as two totally different personalities trying to get out of that dark maze we talked about. One is super cautious, checking every single corner. The other is impulsive, just picking a direction and running with it. And this is the fundamental clash between our first two big strategies, breadth-first search and depth-first search.
So let's start with a cautious one, breadth-first search, or BFS for short. This is our methodical planner. Imagine you're at the starting point. Instead of just picking a path and hoping for the best, BFS looks at all of its immediate neighbors, every single option just one step away. It checks all of them. Only when it has explored that entire first layer does it then move on to the next layer, all the neighbors of the neighbors. It expands outward like ripples in a pond, one complete circle at a time. It never gets too far ahead of itself, making sure it doesn't miss an easy solution right near the start. The way it keeps track of this is with what's called a first-in, first-out queue. It's just like a line at a grocery store. The first spot you add to your to-do list is the first one you explore.
Okay, so what do you get for being so careful? Well, you get two huge guarantees. First, it's complete. That means if a solution exists anywhere in the maze, BFS will find it. Guaranteed. Second, it's optimal, which means it will find the shallowest goal, the one with the fewest steps. Awesome, right? But, and this is a massive but, look at the cost. The time and space complexity is OB to the power of D. Let's break that down because it's really important. B is the branching factor, how many choices you have at every step, and D is the depth of the solution. So if you have, say, 10 choices at every step, and the answer is 10 steps away, that's 10 to the 10th power. That's 10 billion nodes you might have to check. But the time isn't even the worst part. The real killer, the reason BFS often fails in practice, is memory. To explore layer by painstaking layer, it has to keep that entire last layer in memory. And that number grows exponentially. It will almost always run out of RAM, long before it runs out of patience. All right, now let's flip the script completely and look at the other personality, depth-first search, or DFS. This is our impulsive explorer. DFS doesn't waste time checking all its options. It picks one path and just goes for it. It dives as deep as it possibly can, sprinting down one long hallway, making turn after turn, until it either finds the goal or hits a dead end. If it hits a wall, no problem. It just backtracks to its last decision point and tries the next path. It's all about exploring one branch completely before even considering another. To do this, it uses something called a last-in, first-out stack. Think of it like a stack of papers on your desk. The last thing you put on top is the first thing you grab. That's how it remembers its path and knows where to backtrack to. So what's the trade-off here? Well, DFS has one absolute undeniable superpower, its memory usage. Look at that space complexity. Because it only has to remember the one single path it's currently on, it is incredibly light on memory. It's a game changer. But, and you knew there was a but coming, that speed and efficiency come at a really dangerous cost. First, it is not complete. What does that mean?
It means if your maze has a loop, DFS can literally get stuck running in circles forever, never finding the exit even if it's right next door. And second, it's not optimal. It might find a solution, but it could be a ridiculously long, winding, inefficient one simply because that's the first one it stumbled upon. It has no concept of finding the best path. So here's where we stand. We've got two polar opposites. BFS is the safe, reliable one. It's guaranteed to find the best solution. But it's a memory-guzzling monster that might not even be able to run on big problems. Then you have DFS, which is lean, mean, and super memory efficient. But it's reckless. It can get lost forever or bring you back a terrible answer. So you've got safe but slow versus fast but reckless. Clearly, neither of these is the perfect solution, which naturally leads to the next question: can we somehow get the best of both worlds? Before we try to combine them, let's add a little wrinkle to our problem. So far, we've been assuming that every step is equal. Every door takes the same amount of effort to open. But that's not how the real world works, is it? If you're planning a trip from New York to LA, not all paths are created equal. Taking a direct flight is different from a route with 5 layovers. The number of steps doesn't matter as much as the total cost, whether that's time or money. This simple idea leads us to a smarter way of searching by cost. And this is where an algorithm called Uniform Cost Search, or UCS, comes in. You can really think of it as a much smarter, more sophisticated version of breadth-first search. It doesn't just expand the shallowest node. Instead, it always expands the node that has the lowest total cost to get to from the starting point. So it keeps a running tally for every path it's found, and it always picks the cheapest one to explore next. To manage this, it doesn't use a simple line. It uses a priority queue, which is basically like having a constant VIP line. The node with the lowest cost always gets to jump to the front, no matter when it was discovered. And here's the really cool part that ties it all together. If all your step costs are identical, let's say every move costs exactly 1 point, then UCS behaves exactly the same as BFS. The shallowest path is the cheapest path, so they do the same thing. But the second you introduce variable costs, different road distances, fluctuating plane ticket prices, that's when UCS really shines. It's guaranteed to find the path with the lowest possible total cost. It might have more steps, but the final bill will be cheaper, and that's what makes it optimal in a much more useful real-world sense. Okay, so Uniform Cost Search is a great tool for handling real-world costs, but it still has that same Achilles heel as BFS. It's a memory hog. So we're back to our original dilemma. We want the optimality of BFS, but we desperately need the tiny memory footprint of DFS. Can we have our cake and eat it too? Is it actually possible to combine them? Well, it turns out the answer is yes, with a really clever and kind of weird-sounding algorithm. So let me introduce you to what is often the star of the show: Iterative Deepening Search. Now, I want you to stick with me because how this works sounds incredibly inefficient at first. It feels just wrong, but it's brilliant. Here's what it does. First, it runs a full depth-first search with a depth limit of 0. Basically, it just checks the starting spot. Is that the goal? No? Okay. Then it throws all that work away and starts over. This time, it runs a DFS with a depth limit of 1. It checks the start and all its immediate neighbors. Still no goal? Okay. It throws it all away again and runs a DFS with a depth limit of 2. It keeps doing this, increasing the depth limit by 1 each time, until it finally stumbles upon the goal. I know exactly what you're thinking right now. That is the most wasteful thing I've ever heard. You're just redoing the same searches over and over. And you're not wrong. It is redoing work. But here's the crucial insight, and it's summed up perfectly in this quote from the source material. The search space in these problems grows exponentially. That means that the number of nodes in the very last, deepest level of the search is vastly larger than all the other levels combined. So yeah, you're regenerating those top levels, but they represent a tiny, tiny fraction of the total work. The real heavy lifting is only done once, on that final iteration when the goal is found. The overhead is surprisingly small. And that leads us to the big payoff, the punchline for this whole thing. This weird, counterintuitive approach actually gives us the magic combination we were looking for. Think about it. Because each individual search it performs is a depth-first search, it gets to inherit that incredible, super low memory usage of DFS. But because it's systematically increasing the depth limit, 1, then 2, then 3, it's exploring the space layer by layer, which means it is guaranteed to find the shallowest solution, just like BFS. It's truly the best of both worlds, the memory of DFS with the completeness and optimality of BFS. All right, so we've met the whole cast of characters. We've got BFS, the cautious planner.
We have DFS, the reckless explorer. We've got UCS, the cost-conscious traveler. And finally, IDS, the clever hybrid. It's time for the final showdown. Let's put them all up on the board and compare the stats head-to-head to see who the real winner is.
This table really says it all, so let's walk through it. Look at BFS and UCS. They get check marks for being optimal and complete, which is great. But look at their space complexity. O of B to the D. That's that exponential memory growth that just kills them on big problems. Now look at DFS. Its space complexity is fantastic. O of BM, which is linear, but it fails on optimal and complete, making it unreliable. And then look at iterative deepening. Its time is O of B to the D, just like BFS, which is the price of being thorough. It's optimal, it's complete. And now the knockout blow. Its space complexity is O of B times D. That is linear space, just like DFS. It combines the strengths of everyone else with almost none of the weaknesses. It's a clear winner.
And that leads us to the final verdict. When you are dealing with a huge search space and you have no idea how deep the solution might be, iterative deepening search is almost always going to be your go-to strategy for a blind search. It pulls off this incredible trick of combining the safety and correctness of breadth-first search with the lean memory profile of depth-first search, making it powerful, practical, and robust.
So we've spent all this time figuring out the absolute best way to find our way out of a pitch black maze. But that leads to a tantalizing final question. What if it wasn't pitch black? What if we had a little bit of information? What if we could feel a faint breeze that told us we were getting closer to the exit? What if our algorithm had some kind of hint or a rule of thumb to guide it? In other words, what happens when our search is no longer blind? Well, that's where things get really interesting. That's the world of informed search, and trust me, it changes everything.